Now Rlc Series Circuit. First we are going to we are going to connect resistor and coil. So Rl circuit in series, we are going to study this. First we have to know that electric current is the same through both resistor and the coil and the generator with the same function. I is equal to IM sine omega t. What does it mean? Electric current of the generator is the same as the electric current on the resistor is the same as the electric current on the coil, because electric current in series circuit is the same through all the elements. So that's why we are going to define the potential differences according to with respect to electric current. So electric current will be drawn in the phasor as horizontal because all have the same electric current. So a red line, which defines the phasor for electric current. On a resistor, electric current potential difference are in phase. That's why we are going to divide VR, the potential difference on the electric resistor is in the same direction of electric current. But in the coil, potential difference leads to electric current by pi over t. That's why we are going to draw VL by making an angle of 90 degrees. So potential difference is leading the electric current by pi over t. So this is the phasor for a series connected series RL circuit. So to find the total potential difference, which is the total potential difference is the potential difference across the resistor and coil, we should add them. We are going to add them in a vector, but not in scalar. VL plus VR. We are going to add these phasors in vector. So how to add the vectors? Locate one of the vector first. It is the VR. So add second vector to the tail of the first vector, which is VL. So from the beginning to the end, draw a line. So this is the V total. So how to find the magnitude of V total? It is Pythagorean theorem. We can calculate it. V total is equal to square root of VR squared plus VL squared. So V total can be found by this way. So if we divide, because the electric current is the same through the resistor, inductor, and the generator, if we divide the potential difference by I, for example, VL divided by I, it will give us XL. VR divided by I will give us R. V total divided by R will give us the Z. What is Z? Z is called the total impedance of the circuit. So that's why the resistor and inductive impedance have the same phase angle as the VR and VL. So that's the total impedance. Z can be calculated by again Pythagorean theorem, R squared plus XL squared square root. So as you see, these two equations, these two angles all are the same. How can we calculate this angle between the electric current and total potential difference, or electric current and Z, or ZR and Z? So this is theta. This theta is known as the phase angle difference. So tangent theta can be calculated by opposite side of the triangle divided by adjacent side. Opposite side is VL, adjacent side is VR. So also we can calculate tangent theta from this triangle. Opposite side is XL divided by R. XL divided by R. So both equations can be used for calculating the phase angle difference. Question number 1. A voltage source of instantaneous value V 20 sine 100 pi t is connected across a series combination of a pure resistor of resistance 100 ohm and a pure coil of self-inductance 0.2 Henry. So resistance is given, and the coefficient of self-induction is given. Calculate the total impedance of the circuit and calculate the Z and the phase angle difference between the electric current and the total potential difference. So phase angle difference between the electric current and total potential difference will calculate the theta, tangent theta. So equation for generator is given as V 20 sine 100 pi t. What does it mean? Vm is 20, omega is 100 pi. 100 pi is equal to 100 times 3.14, which is equal to 314 radian per second. So to calculate the Z, we need to calculate equation for Z, R squared plus XL squared, but XL needed to calculate. XL is equal to omega times L. R isn't given, it's 100. Omega L is 314, so write it here. L is given in the question as 0.2 Henry. So 0.2 square of these numbers, answer will be 118 ohm. So it is the total impedance of the circuit. To calculate the phase angle difference, we can use XL over R. XL is calculated, we can calculate XL by omega L. R can be calculated, is given in question as 100. So omega is 314, L is 0.2 divided by 10. So inverse of this number will give us the tangent theta angle between the potential difference of electric current, which is equal to 32.2 degree. Now, RC circuit, if we connect a resistor and the capacitor in series, electric current again the same through the both resistor and capacitor and the generator. So electric current again is the same. That's why we are going to define the potential difference according to with respect to electric current. So in resistor we know that potential difference and electric current are in phase. That's why we are going to draw these two vectors in parallel. But in capacitor, potential difference lags behind. That's why we are going to draw VC down like this. So then add them to calculate the total potential difference across the resistor and the capacitor. VR plus VC is equal to V total. Again, the same equation, VR squared plus VL squared is equal to V total squared. The Pythagorean theorem can be used for calculating the total potential difference. Again, we will divide by I because electric current is the same. Divide by I, and get VR divided by I is R, VC divided by I is XC, V total divided by I is the Z. So these two similar triangles, again from these two triangles we can calculate the phase angle difference theta. So theta is equal to VC divided by VR, VC opposite side divided by adjacent side, or XC divided by R, we can calculate here. Z again the same as this one, R squared plus XC squared is equal to Z squared, or Z is equal to square root of RC plus squared plus XC squared. So a voltage source of instantaneous value 20 sine 100 pi T is connected across a series combination of a pure resistor and resistance 50 ohm and capacitor of 2 microfarad. So 20, 100 pi is the generator, so Vm is 20. If needed, you are going to use omega is 100 pi, so it's equal to 100 times 3.14, which is equal to 314 reading per second. So calculate the total impedance. That is the question. Calculate the total impedance of the circuit and the phase angle difference. To calculate the Z, we know what R is, but we don't know what XC is. We should calculate for XC, which is equal to omega times C. 1 over omega divided by omega times C. Omega 314. C is 2 microfarad, 2 times 10 to the power of negative 6 farad. So 2 times negative 10 to the power of negative 6 farad. The answer becomes 1593 ohm. Now it's time to calculate the total impedance. Z R squared by XC squared. R is given in the question as 50 ohm. So XC is calculated as 1592 ohm. So answer becomes 1593 ohm. It's very close to XC. What about the phase angle difference? It is equal to XC divided by R. XC is 1592 divided by 50. It's almost 88.2 degrees is the phase angle difference. Now we are going to combine the RLC parallel series circuit, but now we are going to combine all of them, not only two of them. So resistor, inductor, and the capacitor all are connected in series. Again, in series circuit, electric current is the same. We are going to start with electric current, and we are going to define potential differences with respect to the electric current. So in resistor, VR and I in phase. In coil, VL is leading the electric current. In capacitor, we see potential difference lags behind. So again, we are going to add them in vectors to find the total potential difference across the capacitor, inductor, and resistor. VR, VL, VC, because VC is in opposite direction of VL. So this is the V total. How can we calculate it? V total squared is equal to VR squared plus this side, this length is equal to VL minus VC. So square of VL minus VC. So this is the equation for calculating the total potential difference. Again, that is calculated in the same form, because when you divide them both with I, you get all the same thing. VR divided by I is R, VL divided by I is XL, VC divided by I is XC, V total divided by is the Z. So this equation, the equations are very similar. Even to calculate the theta, we use the similar equations. Tangent theta is equal to opposite side VL minus VC divided by VR, or opposite side XL minus XC divided by R. So both of them are used for calculating the phase angle difference. Now Z is also very similar to calculation V total. Z is equal to R squared plus XL minus XC squared, which is the total impedance of the circuit. So now a voltage source of instantaneous value 20 sine 100 pi t, so 20 sine 100 pi t. It's connect Rlc circuit, which is R is 20 ohm, C is 4 microfarad, L is 2 times 10 to the power negative 3 Henry. So all are given. 4 times 10 to the power negative 6 farad is the capacitance. So calculate the total impedance Z of the circuit and the phase difference between the electric current potential difference theta. So to calculate ZR is needed, XL is needed, XC is needed. R is given in the question, but XL and XC must be calculated because C and L is given. XC 1 over omega C, omega is 100 pi. From this equation we got this is omega 100 pi, and 100 pi is equal to 100 times 3.14, which is 314 radian per second. So omega times C, so it is XC is 796. XL omega times L, so 314 times L, 2 times 10 to the power negative 3, so it is 0.628 ohm. Now it's time to calculate Z R squared plus XL minus XC, R squared plus XL minus XC, or XC minus XL doesn't make difference because we are going to square it both negative and negative positive cases. Answer will be positive. So this is the Z. For phase angle difference, XL minus XC divided by R, XL is, or XC minus XL doesn't make difference. So if it is XL minus XC is positive, so in this case angle is positive, is XL minus is negative, in this case angle is negative. So XL minus XC, 796 minus 0.60 divided by 200, 200 is the R, it's going in, not 200, 20 is the R. So answer is 88.6 degree. It is the phase angle difference between the electric current and potential difference. Sample problem. It says in the figure 6.28, find the reading of ammeter, voltmeters, and phase angle difference between VR and VT. If VT is equal to 100, 30 volt, and XL is equal to 14 ohm, X is equal to 5 ohm, R is equal to 12 ohm, and F is equal to 50 hertz. In series circuit, we know that the current in each element is the same. We continuously remind this because the same current is flowing through each instrument. All are given, so we will find one by one V on C, V on L, V on R. To calculate them, we need electric current. First, we should start calculating the electric current, but electric current can be calculated only if you find the Z. For that, first you should find Z, what Z is. Z is equal to R squared plus XL minus XC squared. So R is 12, XL is 14, XC is 5, so it is the 15 is the Z. Now it's time to calculate the electric current by using Ohm's law. We total effective potential difference divided by Z. Total potential difference divided by total impedance is the electric current of the circuit. 30 is the total effective current, which is this one, 30 volt. Question says this is 30, so it is the electric potential difference through the all three elements divided by Z is equal to 2 ampere. So 2 ampere is the electric current flowing through these devices. So for that, this meter reads 2 ampere. So now the same electric current is passing through the C, L, and R. Then use Ohm's law for calculating VC, VL, and VR, because the same current is flowing through the C, same current through the L, same current through the I. Just multiply them. 2 times 5, 2 times 14, 2 times 12. So 10 volt is the potential difference on C. This is 10. So 28 volt is the potential difference, and this is 28 volt. So and the VR is 24 ohm is to 24. So now we calculated the potential difference reading of voltmeter 1, 2, and 3. Now next last one. So potential difference on the capacitor and inductor. We need to refer the phasor. As you see in the phasor, VL and VC are in opposite direction. If two vectors are in opposite direction, we should most subtract them to find the resultant. So which one is greater? VL is 28, VC is 10. 28 minus 10. This is 28 volt. This is 10 volt. That's why VLC will be 18 volts. So reading of this voltmeter is the 18 volt. So use the following equation for calculating phase angle difference. Tangent theta is equal to XC minus XL divided by S. XC minus XL is 9 divided by R is 12. It is the 37 degrees. This is the phase angle difference. Next is the parallel connected circuit. So if capacitor, inductor, and resistor are connected in parallel, what is equal? This time potential difference are equal. Yani V, and V. But electric currents are different. IR, IL, and IC are different, and I is different. So I is equal to IR plus IC plus IL. So in vector, we are going to add them again. Total current is equal to current on the resistor plus current on the inductor plus current on the capacitor. So now we will use again phasor vector addition method to find the answer. Okay, so now let's start. First, if the potential differences are equal, IC, IL, and IR can be calculated very easily because IR is equal to V divided by R. IL V divided by XL, IC V divided by XC. I total even can be calculated by the same method, V divided by Z, because all these are equal. So if these are equal, in the phasor we are going to start with potential difference, because potential difference is the same for all element, and we are going to define the electric current with respect to potential difference. Let's start with the resistor. In resistor, potential difference and electric currents are in phase. In coil, which one is leading? In the coil, potential difference is leading the electric current. The electric current is lags behind. That's why we are going to draw IL lags behind the potential difference. So by 90 degrees or pi over 2 radian. So what about capacitor? In the capacitor, electric current is leading the potential difference pi over 2. So this is the phasor, current phasor, electric current phasor for parallel connected Rlc circuit. So now let's, for calculating total electric current, we should add the currents in vector. Start with IR. IR is in horizontal. IC is positive y direction. IL is negative y direction. So I total is the addition, vector addition of these three vectors. So it can be calculated by this equation, Pythagorean theorem. So IR squared plus IL minus IC squared is equal to I total squared. So this is the equation for calculating total current. Also, we can calculate total current by effective potential difference of the capacitor or the generator divided by Z. This is also possible. So according to question, you can use one of these equations. Phase angle difference is from this triangle can be calculated. Opposite side of the angle is IL minus IC. So tangent theta IL minus IC or IC minus IL divided by R. This is the equation for calculating phase angle difference. So what about the impedance? So impedance also can be calculated with similar way. In series combinated circuit, it was, remember, Z is equal to root of R squared plus XL minus XC. This is in series. In parallel, so as you see, everything is 1 over. 1 over Z is equal to root of 1 over R squared plus 1 over XL minus 1 over XC squared. So by this method, you can calculate the total impedance of the circuit. Let's do a problem. In your question, there is one problem about this. So it's the mixed review question. It says an AC source of effective value of 50 volt is connected across a parallel combination of resistance 300 ohm, an inductor of impedance of it is XL 600 ohm, and capacitor impedance is 200 ohm. Calculate the following. Impedance of the circuit. Equation for calculating impedance is 1 over Z equals 1 over R squared plus 1 over XL minus 1 over XC squared square root. So write numbers and be careful. You will first calculate 1 over Z, then you are going to 1 over both sides of the equation and you will calculate the Z. After calculating Z, calculate the effective current of the circuit, because you know what effective potential difference is. It's given in the question. Effective potential difference is 50 divided by Z. Z is calculated 213. 50 divided by 213 is equal to 0.23 ampere. So it is the electric current supplied by the generator to the circuit. But this is the effective current, it's the answer of C. But for B, effective value of the current that passes through the resistance, inductor and capacitor should be calculated one by one. So because the potential difference are the same for each of them, IRV divided by R, ILV divided by XL, ICY divided by XC, V's are the same, so 50, 50, 50. R is different, XL is different, XC is different. So you will find the answer one by one for IL, R, IL, and IC. Right after that, you can calculate the phase angle difference, because remember, phase angle difference is equal to IL minus IC divided by IR. So write numbers here. 0.25 minus 0.083 divided by IR, 0.167. So answer is 45 degrees. Okay, next title is the oscillating circuit. So what is an oscillating circuit? An oscillating circuit consists of a capacitor and an inductor. So capacitor is variable capacitor. This sign represents the variable. So initially this capacitor is empty, completely empty. But later you connect this capacitor to a battery and you charge this capacitor by one plate positive, the other plate is negative. In this case, all the energy will be stored in the capacitor and in the form of electric field. However, when you connect this capacitor through the inductor, a coil, so the electric current will start flowing through this coil, and the capacitor will discharge. So, and both plate will be neutral, again uncharged. So in this case, all the energy will be transferred from capacitor to the coil. So the energy will be stored in the coil in the form of magnetic field. However, this coil has an opposition to the change in electric current. Normal electric current must become zero at the end. However, remember, coil reacts in such a way that it always opposes the change in electric current. Because electric current of the circuit wants to becomes zero, this coil produces a current in the same direction of decrease in electric current, and again causes the charging of capacitor, but in opposite polarization. Right here, the polarization is left is positive, right is negative, but right after that discharge, so polarization of the capacitor changes. One left is negative, right is positive. So what does this? The coil does this. But this capacitor must discharge again right after the charge. So from positive to negative, again electric current stays or starts flowing. So this oscillation from right to left blade, from right to left to left to right to left, so continues infinitely if there is no loss of energy. So this circuit is known as oscillating circuit. The frequency of this oscillation can be calculated by this equation. So this in the, XL and XC is equal to each other in this case. So omega L and 1 over omega C are equal. So omega becomes from this equation 1 over root of LC. Because omega is equal to 2 pi F, so this frequency of the oscillation becomes 1 over 2 pi root of LC. So this for F is the frequency of the electric current oscillating electric current in this oscillating circuit. So it depends on L and C, as you see. By changing L or by changing C, you can change the frequency of the oscillation. It is not so easy to change the L, but it's easy to change C by using variable capacitor. That's why it's variable. By changing the area of the capacitor plate, you can change C, and then you can change the oscillation frequency of this oscillating circuit. However, in reality, no circuit is perfect, no circuit is ideal, so energy will be lost. But if you want to continue this oscillation without damping, you should introduce some current to the circuit. But this introduced current must have exactly the same frequency of the oscillation. In this case, you can add energy to this circuit. If a current of the same frequency or phase is introduced in the circuit, resonance takes place. So in this case, we say resonance. What is resonance? So one system adds energy to the another one if their natural frequencies are equal. Remember chapter 3. So by changing the capacitance of the variable capacitor, the resonance frequency can be changed. This is how one can tune the frequency of the radio and television stations at home. When resonance takes place, the reception of the radio signal is possible. So in this oscillation in electromagnetic waves in air, remember all radio stations emit electromagnetic waves. When the frequency of this electromagnetic wave is the same of your radio's frequency, so then the electric current or the electromagnetic waves can be picked up by your radio and you can start listening that music. So next title is the transformers. Transformers are working on the principle of mutual inductance. There are two coils, as you see. Generally, they are used to step up and step down the potential differences. The device that changes smaller AC to a greater AC, which is called as step-up transformer, or a higher AC to a smaller one, which is known as the step-down transformer. So they are called transformers. Right here, as you see, there are two coils. One of them is known as the primary coil. Second one is known as the secondary. One of them is the primary coil right here. The second one is the secondary coil right there. So there is an soft iron core. This soft iron core has a very important function. All the magnetic field lines flows through this the coil. So that's why the magnetic flux through the primary and secondary coil are the same. If the magnetic flux are the same, in this case, because magnetic field in the iron core and the cross-section area of the core are the same for both coils, the potential difference across the two coils depends on number of turns in each coil. So V2 is the number of turns in the secondary, V1 is the number of turns in N2 is number of turns in secondary, M1 is number of turns in primary. So N2 divided by M1 will be equal to V2 divided by V1. V2 is the potential difference in the secondary, V1 is the potential difference in the primary. So as you see, according to the number of turns, you can step up, increase the potential difference, or decrease the potential difference. So if N2 is greater than M1, V2 is greater than V1, so it's a step up transformer. So secondary potential difference is greater than primary potential difference. If N2 is smaller than M1, in this case V2 is smaller than V1, it's a step down transformer because potential difference in the secondary is smaller than potential difference in the primary. N2 or M1 is, this ratio is known as the conversion ratio of that transformer. In this case, if the conversion ratio is greater than 1, so in this case it's a step-up transformer. If conversion ratio is smaller than 1, in this case it's a step-down transformer. So transformers are used in AC circuit because they only induce a magnetic in this current by changing the magnetic flux. And you remember, magnetic flux can be changed only by AC circuit, alternating current, or just pulsating direct current. In a transformer, transformers never increase the power. So power of the primary coil and secondary coil in ideal system are equal. So transformers input power in the primary coil, power in the primary coil, and output power, primary and secondary coil, for an ideal transformer are equal. That's why we are going to write this equation: power input is equal to power output. Power equation is for the electrical devices V times I. So V1 times I1 is equal to V2 times I2. What does it mean? If you step up the potential difference, you are going to step down the electric current. So if the potential difference in the secondary increases, electric current in the secondary must decrease. If a transformer increases electric potential difference V on the secondary coil, electric current on the secondary coil proportionally decreases by the same ratio. But energy is not the same in input and output, because nothing is ideal, but energy is lost because of the small current in the iron core and also heating coils. For that reason, power output is smaller than power input in practical use. Hence, the energy of efficiency of transformer is between 90% and 99%. So transformers are used in electronic ignition system of a car. Remember, in electronic ignition system we use 12-volt battery. This is DC battery. So because it's DC, this transformer only can work when you switch on and switch off the circuit. That's why when you switch off your car by a key, you start your car, because this transformer in the system has a greater number of secondary coils. So the number of primary coil is, if it is 12 turns, secondary is 30,000 turns or something like this. So that's why the secondary coil is increases the potential difference to have very big value and makes a spark inside the cylinder of your car, inside the engine of your car, and starts burning. So when ignition switch is on, 12-volt DC potential difference is converted by an ignition coil, which is a transformer, to a potential difference large enough to cause sparkling and burning the fuel in the engine. So this is in fact very similar to title in mutual inductance, chapter 6, section 2. Okay, so questions about transformers are not so difficult. A state above transformer is used on a 120 volt line of provide potential differences 24,000 volt. So it is in this case 120 is the primary coil, and the secondary coil is 24,000. So it's a stepped up transformer. It says if the primary is 75 turns, calculate how many turns in the secondary have. N2 over M1, V2 over V1. So N2 becomes, in this case, cross multiplying V2 divided by multiplied by M1. So, and according to this equation, you can get the answer as 1,000, 15,000 turns. So now, as I said, transformers are increasing the potential difference, but they do not increase the power. Power in the input and power in the output is the same, almost the same, because of some heating it decreases. But right after this transformer, we use the wires to transfer energy from the power plants to the stairs. Electricity is transferred from power stations to the houses by means of cable negros. You have seen these cable negros, I think, because they are very long. Because this cable stretched hundreds of kilometers, its resistance is quite big. Remember, resistance in the line class is proportional to length of the conductor, because length of these wires are very big, so resistance is big. This big resistance gives rise to the loss of part of the carried energy. Remember, energy loss is equal to I squared times R multiplied by time T. So as you see, if the current is big, energy loss is big. But if you make the current small, then energy loss will be small. That's why we should decrease the electric current while transferring the energy from the power plants to the houses. The energy loss is directly proportional to R, but directly proportional to square of the current. Current has a large effect on the energy loss. So then By stepping potential difference, we increase the variable level, we saw electric current is minimized. Remember, if the potential difference is step up, electric current will be step down. So that's why we are using the step-up transformers right before we send the power from power plants to the cities. In this case, energy efficiency will be efficiency, all types of efficiency, power received divided by power sent multiplied by 100. If power received is equal to power sent minus power lost, so divided by power sent, this will be a equation for efficiency of that system. Now let's solve a problem about this. It's a simple problem. The power in the secondary coil of a power station is 1 megawatts. In the secondary coil and primary coil, so these powers are almost equal, remember. In fact, in reality it's not, but it's almost the same, similar to the idle system. So power sent is equal to 1 megawatt, which is equal to 10 to the power 6 watt. So the station sends the current to the city by means of the cable of 10 ohm resistance under a potential difference of 10 to the power of 5 volts. So this is the potential difference sent. So potential difference sent is the V2, I mean the potential difference in this secondary, 10 to the power of 4 watt. So like if the resistance of the wires is 10 ohm, calculate the transfer efficiency. What is the efficiency? We will find this. First we should find the current sent, because by using current sent we will calculate the power loss. So how can we find current sent? Because by using the power. Power in the secondary is equal to potential difference on the secondary multiplied by electric current in the secondary. Electric current in the secondary is equal to power in the secondary divided by potential difference. Power in the secondary is given as 10 to the power of 6 watt, which is 1 megawatt, divided by potential difference 10 to the power of 5. So it is the electric current is 10 ampere. So so then you can think your circuit is something like this. So from generator the electric current is coming to the primary coil. From the secondary coil we got this, so sent to the steam. So by on a line whose resistance is 10 ampere, this is impossible. 10 ampere resistance is so long distances, but it's a question. Right here we send this power by electric current, which is equal to 10 ampere. So because of this resistance, there will be a power lost. So we will send here power, will be sent here, and we will get some power here power received. So then we will find the energy efficiency. First we should calculate what is power lost. Power loss is equal to I sent squared times R. I sent is 10, R is 10, so 10 squared times 10, it becomes 1000. Now we can calculate the efficiency. Power received divided by power sent, but power received is equal to power sent minus power lost. Power sent minus power lost divided by power sent. 10 to the power of 6 is sent, 10 to the power of 3 is lost. So 10 to the power of 6 is 10 multiplied by 100 is 99.9% of the efficiency of such a system. Calculate the power lost as heat in a wire of resistance to 120 ohm when travels the current of 50 ampere. Very easy. Current squared times resistance is the power lost. It is current is 50, resistance 120. Answer is 3 times 10 to the power of 5. If a power of 3 megawatt is sent along a wire in item 1 right here, so calculate the power at the end of the terminal of the wire and transfer efficiency. So this is power sent. So 3 megawatt, 3 times 10 to the power of 6 watt. So how much is lost? It is in the first question is calculated. 3 times 10 to the power of 5 watt is lost. So first calculate power received. Power received, power sent minus power lost. 3 times 10 to the power of 1 is 6 is sent. 3 times 10 to the power of 5 is lost. So answer is 2.7 times 10 to the power of 6 is the energy received. Calculate the efficiency. Efficiency is equal to received divided by sent multiplied by 100. Received is 2.7 times 10 to the power of 6 divided by 3 times 10 to the power of 6 multiplied by 100. It's almost 90%. Sectional question. This first question is very easy, so you can calculate it. Question 2. Why do we charge a capacitor under a DC voltage only? Because if you use an AC is something positive and negative, positive and negative. If in positive capacitor is charged, in negative it's discharges. Again charges, again discharges. For that reason, so you cannot use AC for charging capacitor permanently. What is the average value of the current over one cycle of AC signal? Average is calculated by adding the numbers and divided by 2. But these numbers, one of them is positive, the other one is negative. When you add them, they become 0. For that reason, the average value of the current over one cycle is 0. This is one cycle. But if you increase the cycle, if you say that to 1.5 cycle, it is not 0 in this case.